Welcome, ladies and gentlemen, to your first lesson on kinematics. Remember, kinematics is a fancy physics word for studying motion. On the screen, you'll see here six physics phrases or words that we use to describe motion. You'll want to be comfortable with the definitions of each of these by the end of this lesson. So let's get started. We're going to work through all of these concepts that you see on the screen by studying one example problem. You see on the screen our example that we're going to study. This is about a runner, and it gives you some information about her motion. She runs 200 meters east, then changes direction and runs 300 meters west, and it takes her exactly 1 minute to do this, and it asks you to calculate the average speed and the average velocity. So what we'd like to do first actually is to bring our previous knowledge up to this point, our newly found knowledge of motion graphs. We want to bring that together with this example. I challenge you right now to come up with the motion graphs, the position time graph and the velocity time graph that matches this woman's motion. And notice that in this case we do have some number information, so we could actually put some numbers on the x and y axes of our graphs. So I'm going to give you a minute to think about that, and then we'll come back and see how you did on your graphs. By motion time graphs, I mean what you see over here on the right side, a PT, a VT, and for the hardcore among you, an AT graph. I know we haven't done this in the graph matching lab yet, but my IB students and AP students will be interested in this, and those physics students who are extra motivated. So we want to be able to sketch graphs of motion for this woman's running. And if you remember from the lab, it's very important to establish which direction is positive. So as you draw these graphs, you want to think about which directions are going to make sense to be positive. In the lab, away from the detector was positive and toward the detector was negative. It really doesn't matter. You, the physicist, gets to choose. In this case, I'm just going to choose east to be positive because that was the first direction that was indicated. But you could choose west to be positive as well. So let me draw that right here. We can just indicate that like this, draw an arrow, write positive, and then in parentheses east. Okay. Okay. All right. So now you know which way is positive. Again, I'm going to I encourage you to pause the video now and to think about what these motion graphs over here are going to look like. Okay. So pause the video, make a sketch, and then come back here in a minute. Click play again, and we'll talk through the results. Okay. You see on the screen here the results of this motion. She moved in a positive direction, so you see this right along here. Okay, she moved in a positive direction at constant speed. Now, it doesn't actually tell us that, but there's no reason not to assume that she ran at a constant speed one way and then the other way. So we're just going to assume a constant speed in a positive direction. She abruptly turned around and ran in the negative direction, and notice that she actually went past the origin, right? She actually ended up to the west of where she started. So we're actually going to go below the line. This is not a possibility in the lab because if you think about it, the motion detector could not detect any motion behind itself. But it is possible to have negative position. Okay. Now we come down here and we look at her velocity. Remember, velocity is speed plus direction. So we see here a constant speed in a positive direction. Therefore it's a constant velocity, and then an abrupt change, and then a negative velocity, right, going in the negative direction. And notice that this red arrow, this red line is as high above the zero axis as this is below, okay, because we're assuming a constant speed at the same time, just a different direction. All right, and then finally down here, for those of you that want to consider the acceleration, she's really not changing her speed the whole time, except for very briefly right here there's a spike in the negative direction, right? If you think about what it takes for her to change from the east to the west. If you come over here, she's running to the east, and all of a sudden, boom, she's heading to the west, right? She's heading to the east, and then all of a sudden, boom, she's heading to the west again. That's going to take a push in the negative direction, and therefore a spike in acceleration in the negative direction. We can actually write some numbers on here. We know that she went 200 meters to the east, so we can actually come over here and write 200, right? And we can come down here. We know that she went 300 meters west. If you think about that, that's a negative 100 meters, right? That's 100 meters in the negative direction that she ended up. Over here, we can't fill these in yet, but we will be able to after we do a little bit of math. So there you have it. There are the motion time graphs, and what we need to get to now is some of these definitions, some of these words. We're going to apply some of these words to this motion. Okay, on the screen here you see the definition of speed. It's just taking the distance traveled by the object, dividing it by the time. However, to understand this, you need to understand what distance is. So let's define distance. Distance is actually the length of the path taken. Okay, length of the path taken. So think about that in the case of this runner. Okay, in the case of this runner, it's simply going to be, we can even put that in parentheses here, 200 plus 300 equals 500 meters. So in the case of our fearless runner here, she has traveled 500 meters. So if we wanted to do that math, right, we could simply write, let me switch here. Okay, we can simply write speed equals 500 meters over 60 seconds. All right, and we do that on calculator. We'll just abbreviate here. 480 is about, what's that? It's 8 1/3, so 8.3 meters per second. Okay, so that's how you would express the speed of this runner. All right, so we're making progress here. We've figured out the speed of the runner. Now we'd like to figure out the velocity of the runner. Okay, so let's do some more defining. Come down here and let's define velocity. I think perhaps from our graph matching lab you may be able to come up with this definition, but we'll write it here. Velocity is speed plus direction. Okay, so you have to consider that. Actually, you know what? I'm going to define it this way. I'm going to define it slightly different. We'll come back to that. No, that's good. Speed plus direction, but it has an equation definition too. So let me write that instead as displacement divided by time, just to kind of be parallel to the speed definition. Okay, so and then down here we're going to write in parentheses velocity equals speed plus direction. Okay, speed plus direction, and you'll see that in a minute how that works out. So an example of speed is 60 miles an hour. An example of velocity is 60 miles per hour north. I have that additional piece of information. Okay, now we need to come up here and we need to find the velocity. We need to find the displacement. Okay, and displacement is defined as follows. It is the straight line distance. Okay, straight line distance between start point and finish point. Okay, start point and finish point. So if we look up here, I'll put that in parentheses. She started at the, well, the best way to do this would be, you can go 200 meters minus 300 meters equals negative 100 meters. So that's for the case of this problem. So remember, if you come up here, she went 200 meters east and then 300 meters west. So now if we put all that together into the equation, okay, so let's switch to our writing mode here. And let's write that. So we'll say, now we're going to do another calculation. We'll say velocity equals displacement over time. Okay, so the displacement was negative 100 meters. And the time was still 60 seconds. And now we get a couple of different pieces of information from the speed. First of all, our answer is negative. And secondly, it's smaller. Right? It's only, if we go to 2 sig figs here, we'll go to 3 sig figs. Okay, negative 1.67 meters per second. Okay, so we can also write this as 1.67 meters per second west, right? Because in our coordinate system, the negative means to the west. All right, so hopefully you're starting to see, even though we started the year using speed and velocity interchangeably, they really don't mean the same thing. Velocity is a bigger idea that has speed as part of its definition, right? Velocity is speed plus direction. So you can see that when we calculate speed and velocity, they don't actually come out to be the same numbers because truly they're not the same thing. All right, we want to finish with our last two terms, which are, let's go back up to the top here. We want to work on average speed versus instantaneous speed. We can define instantaneous speed as kind of a big word, but it's a pretty easy definition. Equals, you can think of it as the speedometer reading at any instant. Okay, and if you think back on this example, remember that we had no information about this runner's motion during her run. We just assumed that she ran one speed at the whole distance. In other words, that her speedometer said the same thing the whole time. But you realize that that may not be true, right? Maybe a squirrel cut her off, and she had to slow down or speed up, right? And so her speedometer would have dipped or it would have gone up in its reading. But the instantaneous speed is the speedometer reading at any instant. Okay, if you come up here to the speed, right? Just because her average speed was this up here is actually represent her average speed. Okay, this 8.3. So I could even write here in parentheses average speed. Okay, I think you'll realize that if you think about this for a minute, that just because her average speed was 8.3 meters per second, that doesn't mean that her speedometer, if we could equip her with a speedometer, it doesn't mean that her speedometer said 8.3 the whole time, right? Maybe she got tired and slowed down. Maybe she was going downhill and sped up, right? But on average, she was running 8.3 meters per second. Whereas her instantaneous speed, right, could be changing constantly depending on the conditions of her run or whatever she decides to do. So, all right, there you have it. Took us a little bit of time, but we knocked out some pretty foundational definitions of describing motion. Actually, I forgot one more thing. We can come back up here and on this number, right, this represents the speed. We can come up here and we can actually write that on our graph, 8.3, right? So that's what this value represents. And then when she abruptly turned around and changed direction, she went the other way at 8.3.